Now that we've talked about proteins, we're going to talk about a specific type of protein, enzymes. The function of enzymes is to speed up how fast chemical reactions are occurring. And what we're going to do is we're going to kind of make a case for enzymes and why they're necessary. By first stating that chemical reactions are necessary to maintain life. So we constantly need to have chemical reactions happening. And chemical reaction, if just to make sure we're on the same page, what that means is that a chemical reaction is when molecules, one or more, the bonds within them break, and then the atoms that made up that molecule recombine into a new set of molecules, or molecule. Here's how we depict this on paper, and this is going to be just sort of a generic format. A plus B, C plus D. The molecules that are necessary for the reaction to occur are listed to the left of this horizontal arrow, and they're called reactants. Okay? So you can think of like reactants as sort of like the ingredients of the reaction. They're what you need for the reaction to progress. And I kind of think of chemical reactions as almost like cooking, where you're combining your ingredients to make a new product. Likewise, in a chemical reaction, you are breaking the bonds between the existent molecules so that the atoms that make them up can recombine to form new products. Like cooking, you need all ingredients present and in the right quantities in order to make the specified product. And the same thing is true of chemical reactions. You need all reactants present in the correct ratios in order for the reaction to progress. On paper, we illustrate the reaction progressing by this horizontal arrow. So this indicates that the reaction, which can be, the word reaction can be abbreviated RXN, is progressing. So to the left of the arrow is like what you have before the reaction. So before reaction occurs. And then what you have on the right is after the reaction, your new molecules. And these are called your products. You haven't created new matter here. The products are going to be atoms that have the same types and numbers of atoms as were in the reactants, just arranged in different combinations. So an example of a chemical reaction that we'll see a lot in this class that we can just use sort of as a talking point is cellular respiration. Cellular respiration, what it does is it takes glucose. We've talked about how there's a lot of energy stored in glucose, and that energy has to be harvested so that the cell can use it. The whole point of cellular respiration, or the main goal, is to harvest that energy. So we have to have glucose and oxygen as reactants, ingredients, and the products that we produce are carbon dioxide, water, and ATP, which is a type of energy that we'll talk about later. So this is kind of what we really want to get out of the reaction, is we need that energy in order to do work. As you can imagine, this reaction is critical to life because we constantly need energy in order to perform cellular work. No energy, no work, no life. Here's sort of the issue. On its own, this reaction could occur as long as these reactants are present, but it might happen too slowly to sustain life. It's not enough that this reaction happens. It has to happen quick enough to produce enough energy to maintain all of the cellular work that needs to be completed. So we need something to help speed this reaction and other reactions in the body up. One thing that theoretically could speed up the rate of the reaction would be heat. We talked about in chapter 2 that temperature is a measurement of the average speed of the molecules in a substance. So if you increase the temperature of a system, then ultimately you're increasing the molecular speed. Think of it this way. You could make more cake if you walked around your kitchen and moved faster, right? Because you would be combining the ingredients quicker and therefore making the product quicker. Same thing if you increase the temperature in reality with a chemical reaction. All of the molecules will move faster, and as a result, they'll interact with each other more frequently and produce more of the product. Here's the problem with using exclusively heat. One, we talked about the idea that if you add too much heat, then the proteins can denature, which sort of is in contrast to what we're trying to do, right? We're trying to produce things that make the system more efficient. If we denature proteins and make them non-functional, then that could lead to death potentially, so that's not good. 2, heat is not a specific mechanism. It's gonna increase the speed of all reactions, not just the one that you want to increase, so there's no specificity. And sort of these 2 reasons are kind of why we need enzymes. Because 1, enzymes don't denature proteins. They are in themselves proteins. In fact, enzymes are proteins that catalyze, which means speed up, reactions. And we say they do so without being consumed by the reaction, which just means that after speeding up a reaction, they can go on to speed up another reaction. The other reason why they're kind of beneficial or preferred to heat is that they are specific. There's going to be specific enzymes for specific reactions. So there are enzymes that their only job is to speed up the rate of cellular respiration, and they're not going to speed up the rate of any of the other reactions, just cellular respiration. So this gives us specificity. It allows us to increase the speed of one reaction without increasing the speed of another reaction. How do we do this? How are enzymes capable of speeding up chemical reactions? Well, we said that a chemical reaction is when you're going to break the bonds within certain molecules and then allow the atoms to reform into new molecules. In order for the atoms to recombine to form your products, you need to first break the bonds in the reactants. So we'll say it takes a certain amount of energy for the bonds in the reactants to break, and for the reactants to correctly orient themselves We have a name for this type of energy. This energy that we're talking about is called activation energy. You can think of it as the amount of energy it takes to start the chemical reaction, because the chemical reaction isn't going to progress until those bonds within the reactants are broken and the reactants are in close proximity in the correct orientation with one another. What enzymes do is they decrease the amount of activation energy needed for a given reaction. And this diagram is sort of illustrating that by using this barrier. They can see here that the barrier is taller, i.e. the activation energy requirement is higher without the enzyme. The enzyme lowers the amount of activation energy needed, and therefore, since less energy is needed to start the reaction can progress quicker. So a good follow-up question is, okay, how are they decreasing the amount of activation energy? Well, kind of the general statement, so the overview would be that they decrease the activation energy by making bonds within easier to break and correctly orienting reactants. So before we get into the specifics that we have here in the bullet points, let's just kind of point out the different anatomical features of the enzyme, so to speak. And really there's one feature we need to focus on, and that's called the active site. The active site is a groove, an indentation on the enzyme that has a very specific three-dimensional shape. So it has a specific three-dimensional shape that matches specific reactants. In a way, the active site is kind of like a lock. A lock has a specific indentation in metal that fits a certain key, and the reactants are like the key that fit this lock. In order for the enzyme to be functional, it's critical that that active site maintain its shape and that it be available for reactants. So enzymes are going to lower activation energy by bringing reactants into the correct orientation. So if the reactants need to be oriented in a certain way for them to recombine, then they're going to make that happen. They're going to kind of bring them into the correct position in that three-dimensional shape. Sometimes the activation site has a slightly different environment than the surrounding environment. So for instance, an example might be the activation site. The active site might have a lower pH, might be more acidic than the surrounding area. Perhaps that lower pH makes it easier to break the bonds within the reactants. And then another strategy is potentially to stress the bonds within the reactants. So here's kind of a good analogy. I don't know why, but for whatever reason at our house, our scissors always seem to be super dull, and I like to crochet, so that means that I'm cutting yarn on a relatively frequent basis. And it's really frustrating when I go to cut a piece of yarn with scissors and the scissors like do nothing, up and down, and no progress. So one thing that I do to kind of combat this is I call my husband over, we each pull one end of the string, and then I go through and cut, and it goes through relatively easy. And the reason why is because when we pull on the yarn, we are stressing the fibers that make up that yarn. And when we stress them, it doesn't take as much energy to break them because there's already being energy exerted on them. It's the same concept here. The bonds are being stressed by the active site of the enzyme, which means that it won't take nearly as much energy for them to be broken, and that lowers the activation energy. Now, there are a series of different factors that will influence how effective enzymes work. We're going to go ahead and break these down. Some of them we've already talked about, some of them we haven't. One thing that will influence the effectiveness of the enzyme will be the enzyme concentration. If you increase how many enzymes are available, the reaction rate increases up to a certain point, and then we start to see this plateau. And here's kind of an analogy that sort of explains what we're seeing here. I want you to imagine that you go to the DMV, okay? Let's say you go to the DMV one day, and there are 5 tellers working, and you walk in, and there are 50 people who need help. As you can imagine, there's going to be a wait. This is not going to be a fast process because there's more people who need help than tellers, and you can only have a 1-to-1 ratio. Only one teller is going to help one person at a time, okay? If you were asked to do something to increase the efficiency, what you could say is, well, if we increase the number of tellers, the process will go quicker. So let's say that I increase it by 5 more, and now I have 10 tellers. You've doubled the number of tellers, which means that you should be decreasing your wait time. Now, if you keep increasing tellers, you can keep decreasing the wait time up to a certain point, right? Up to the point that you have 1 teller per person. If you have 60 tellers and 50 people who need help, having the extra 10 isn't going to make it any more efficient. There's still only going to be one person helping you at a time, and they're going to help you immediately that you walk in the door. So having the extra tellers not helping anybody isn't going to increase your efficiency. Likewise, if we have more enzyme than reactants, then that's not going to make the reaction go any quicker. The reactants need to be present in order to increase the speed, and so having more enzymes than reactant is going to be what leads to this plateau. Temperature also has an effect on enzymes as well. We can see that if we increase temperature up to a certain point, we increase the rate of the reaction. And again, this is due to the fact that an increase in temperature is equivalent to an increase in molecular speed. If the molecules are moving faster, then they can fit into the active site quicker, and then therefore interact with the enzyme faster, causing the reaction to occur quicker. Now, this is only true up to a certain point, and then we see a pretty dramatic drop. What accounts for this decline here is that this is the point at which the enzyme denatures, loses its three-dimensional shape. We said that proteins denature at extremely high temperatures, and so if you reach sort of that tipping point, then the enzyme is going to lose its three-dimensional shape and no longer be able to speed up the chemical reaction. pH is also a factor that can influence the efficiency. Enzymes have a specific range of pH, that is what we call like their functional range. A range of pH that they can be effective within. If you go outside of the range in either direction, then they can denature. Now, one thing I just want to point out is that the range is not identical for all enzymes. For instance, the enzymes that are in your stomach, which is a really acidic environment, their range is probably shifted much lower on the pH scale than, say, enzymes that are floating around in your blood. And then finally, the presence of inhibitors or activators can also have a big influence. Adding activators, equals an increase in efficiency up to a certain point. And the opposite is true of inhibitors. Inhibitors decrease the efficiency. So let's talk about what these are and how they're influencing the enzyme. And we'll start with inhibitors first. Inhibitors, just by name alone, kind of indicate that they're not going to have a positive effect on the effectiveness of the enzymes. If you inhibit something, that means that you're stopping or hindering it. So inhibitors, they stop enzymes from speeding up chemical reactions. And to explain how they do that, I want to kind of contrast what the inhibitor does versus what would normally occur without the inhibitor. So here's kind of our illustration of our normal effectiveness. The purple is the enzyme in this illustration, and the blue or the teal right here, this is the reactant that is supposed to be worked upon by this enzyme, and this sort of groove right here, that is the active site. So as we have said, how the enzyme should normally work is that the reactant should fit into the active site, and once they bind together, that's what will speed up the reaction by breaking the bonds within the reactant so that it can reform to the products. The first contrast that we're going to look with this, or the first type of inhibitor, is called a competitive inhibitor, and the inhibitor in this image is the blue shape. Competitive inhibitors, the word competitive means that they compete for the active site. They are molecules that don't fit the active site's shape like the reactant does, but they still bind in that space. And what they do is they block the intended reactant from the active site. If the intended reactant can't fit into the active site, then the reaction that reactant is for cannot be sped up. Now on the flip side, we have non-competitive inhibitors, or they're sometimes called allosteric inhibitors. In this image, the inhibitor is this orange shape. With an allosteric inhibitor, they're not going to bind to the active site. So they bind to the enzyme somewhere other than the active site. The problem is, even though they're not bound to the active site, when they bind to the enzyme, they distort the shape of the active site. This then distorts 3D shape of active site. Reactant no longer fits. So we can see that in this image, the binding here sort of caused this to sort of splay outwards, and now the reactant doesn't fit in the active site, and the consequence is the same. Regardless of whether you have a competitive inhibitor or an allosteric, aka non-competitive inhibitor, the same outcome is true, in that the reactant won't fit into the active site and the reaction won't be sped up. Activators are the opposite, okay? So activators are going to help the enzyme speed up the chemical reaction. We have two different types of activators that are sort of analogous to the two different types of inhibitors, cofactors and coenzymes. Really the only difference, they both do sort of the same thing. Cofactors tend to be inorganic substances, and coenzymes tend to be organic substances. But really, their function is the same. They are molecules or entities that bind to the active site. This binding allows for an ideal fit with reactant or reactants. So the cofactor, the coenzyme, actually is facilitating the binding of the reactant to the active site. It's making it fit well into that space. And so it's really necessary for the enzyme to speed up the reaction. An allosteric activator. The word allosteric in these cases refer to the binding to somewhere other than the active site. And in this image, it's down here in this space. So allosteric activators bind to somewhere other than the active site, thus stabilizing the 3D shape of the active site. So in this case, a minute. Sorry about that. So in this case, the presence here stabilizes shape of active site so that the reactant fits the way that it's supposed to. So overall, the inhibitors, they stop the enzyme from functioning, they stop it from speeding up the reaction because they keep the reactant from the active site. The competitive inhibitors block the reactant site. The allosteric inhibitors, they distort the shape of the active site by binding somewhere else in the enzyme. Cofactors and coenzymes are sort of analogous to the competitive inhibitors because they are binding to the active site. So in both the competitive inhibitors and the cofactors coenzyme, both of these bind to active site. That's what they have in common. The difference is one of those bindings is facilitating the reaction and the other one is stopping it. And the non-competitive inhibitor, or the allosteric inhibitor and the allosteric activators, these are binding to somewhere other than the active site. In the case of the inhibitors, that's distorting it and making the active site non-effective. In the case of the allosteric activators, that's stabilizing the shape of the active site and allowing it to work the way it's supposed to.